Hello everyone and welcome back to the channel. Today's experiment is to jump out of a plane to test 3 different sensors and measure the performances of a skydiving canopy. We are at the drop zone and look at all the parachutes we have here. If you want to know more about this topic, let me know, I'm gonna do a video about it. So this is device number 1, which is a pitot plus airspeed sensor plus a GPS. Then we have device number 2, actually we have 2 of those, and this is a device designed specifically for skydiving application, and that's my gear that I'm gonna use today. I'm gonna put one of these GPS inside of my canopy with a special pocket that I designed. I hope I don't lose it when I open the parachute. This device also has accelerometer, gyroscope, a barometer, and other sensor. I'll show you later how to use them. Now it's time to get on board. Today I'm gonna jump out of a skyvan. You can run out of it if you want to. I'm the last of this load because I'll open a bit higher my parachute because I have to do some canopy tests. So I have to wait everyone to jump before me. Look at the view, pretty amazing, isn't it? Finally, it's my turn. Say bye to the plane, check the altitude, and open the parachute. This was a bit of hard opening, to be fair. Check the altitude again and look for the landing area. During this jump I was wearing 3 devices in different parts of the body and the gear, and this one is one of them, and I have attached it to a special belt I designed. Now it's time to land. I hope I got good data because you never know what can happen. Maybe the GPS loses the signal with the satellites and I have to jump again. If you look at this is the belt that holds my airspeed sensor, and now it's time to go back to the office and I want to show you some results about this jump. Alright, we are back at the office. So as I said before, the main goal of this video is to measure the performances of my canopy. To do that, I've been using 3 different devices. 2 of them were a combination of GPS, accelerometer, gyroscopes, pressure readings, so like a barometer, and temperature sensors as well. And I had another one which was an airspeed sensor which I designed, and a combination of all those 3 instruments placed in different positions of my gear and the canopy are gonna give us some pretty amazing results that I'm gonna show you right now. So first of all, we wanted to measure the pressure and extrapolate the altitude at which we were flying. So as you can see from this, at ground zero, when we were on the ground, the barometer was reading around sea level conditions, so a bit more than 100,000 Pascal, and as you can see, the pressure starts to drop when we go up with the plane. We go up around 4,000 meters, and that's the point where I jump out of the plane. This is the free fall. So as you can see, in a very short amount of time there is a lot of drop in altitude, and of course the pressure goes up again, and this change in the inclination of the curve, the line, sorry, is the opening of the parachute. This is the part of the flight where I was flying my canopy, and that's the landing again. Of course, pressure and altitude are strictly related by a formula. If you want to know which one, let me know, I'll write it into the comments. So let's start now to analyze the data coming from the accelerometer, because if you want to look at the performances of a canopy, like lift coefficients versus angle of attack, we have to calculate that angle. And how do we do that? Using accelerometer and gyroscopes. So we have X, Y, and Z axis of the device I put inside the canopy. This is the timeline of the whole jump, and those are G's. So divided for the 3 axes. I didn't have the total one here, but just to give you an overview of what all those data are giving us, which this is the synchronization phase. So when I was on the ground, all these messy data here are the ones where I was packing the parachute and the GPS was inside of it, so those data cannot really tell us anything. This is the part of the flight where I was going up with the plane, so I was sitting inside the plane with no main acceleration. This is the part of the free fall, and this is the opening of the parachute. So as you can see, in each axis we have a lot of G's while pulling the parachute, around 4 more or less. That's after that we have the canopy part of the flight and then the landing. Let's zoom in a little bit. So as I said, this little portion right here is the free fall. Then we have the opening of the parachute, a lot of other input and acceleration during the flight, and then we have the landing. We also have a gyroscope because, as you may know, if you want to calculate pitch, roll and yaw angles, those are the 3 main angles used in aeronautics. We can extrapolate the pitch and roll from the accelerometer, and usually the gyroscope is used to calculate the yaw. I mean, there are many different ways to do that, but that's a pretty common one. So gyroscopes is giving us degrees per second. As I said before, we have an initial phase where I was synchronizing the devices. So I was putting those devices on a flat surface for more or less a minute, try to see if there are any background errors, some noise that I have to remove afterwards. Then we have the plane part, that's the opening of the parachute and fly and then landing. Let's have a look how about the angles. So as I said, pitch, roll and yaw angles. On the left we have the data as they have been recorded, so with no filter, with no removing of noise, anything. So pitch and roll, as I said before, comes from the accelerometer readings, while the yaw angle comes from the gyroscopes. There are a lot of theory behind how to calculate those angles. I'm gonna link a couple of articles that explains a lot about it, but basically you can find those 3 angles in many different ways. The way I did it was using the accelerometer for the first 2 and the gyroscope for the third. Anyway, as we can see, we have pretty good readings for the first 2, but there is something going on for the yaw. The yaw has an incremental error, so in this part where I had basically 0 roll, 0 pitch because I was sitting inside the plane without moving, the yaw was still going up, and this is due to the way the yaw is calculated. This is kind of an incremental error that must be fixed. So to fix this kind of background errors that I have, I use first a pitch and roll correction also for the yaw, and then I've applied some filters. For the first 2, those filters works pretty well, but for the yaw still I couldn't get any good data, because as you can see here, I should get data between 0 and 360 degrees. I was getting a lot more, so 2500 degrees, which is insane. So in order to correct this, I have to use also a magnetometer, because if I can calibrate my gyroscope with a magnetometer, I can fix those errors. But that wasn't the point of this video, because the only thing that I needed was the pitch. So without wasting any time, I'm gonna show you another zoom in about the pitch. So this is on the left, the pitch data without any filtering. So as you can see, if this is the first minute where I was holding the device on a flat surface, more or less at 0 degree. You can see we have some noise because I was expecting an angle of around 0 degree, but we have 2.25 degrees of error. So first thing to do is to remove, with this blue line pitch corrected, this kind of noise, background noise we have. So after you take this, you make the average of the first, I don't know, 60-80 seconds, and you remove those average from these readings, and you get this new data right here, the blue line. But since we have some peaks, I decided to smooth using a filter, and that's what the orange line represents. I did the same also for the roll, of course. This is basically what you do when you want to tune your instruments before using it. So if you want to calibrate your instruments, make sure to leave it on a flat surface for 30 seconds, 1 minute, and do this kind of math post-processing afterwards. If we zoom in on the yaw, in the first 60-80 seconds, without moving the device, we were having a angle increase from 0 to up to 400 degree. I tried to correct it a bit. Results were a little bit better, but still after 80 seconds we had a 20 degrees error, so that was too much. As I said, we need to implement a synchronization with the magnetometer, and probably this error is gonna disappear. So why do we need all of that to calculate the performances of a canopy? We must look for the angle of attack. So in order to get the angle of attack for a canopy, we have to find it coming from two other angles. The red line you see right here is the pitch. So this one right here I was showing you before. The green line is the trajectory line, and this comes from the airspeed sensor and the inclination of the trajectory that I had with that instrument. If we combine the two, we get the blue line, which is the angle of attack. So angle of attack comes from the sum between the trajectory angle, which is the green line, and the pitch angle. The science convention depends on what your reference system is. This line here represents the velocity recorded from my airspeed sensor, which I called pitot speed in kilometers per hour, which you can read here. So I was flying at around 50 kilometers per hour with my canopy without pulling any brakes. When I decided to pull a little bit the brakes, so change the shape of my canopy, what I did was slow down at around 40-35 kilometers per hour, and my angle of attack went up, and that was the thing that I was expecting. So this is a good sign. Again, I was holding my brakes for a few seconds, and again slow down a little bit, pulling much more the brakes, going to a condition very close to the stall of the canopy itself. And again, velocity was around 30 kilometers per hour. My angle of attack increased again, and as you can see here, the angle of attack increases because of the trend and the combination between the trajectory angle and the pitch. The pitch is the angle recorded by the GPS inside the canopy, and the green line, so the trajectory angle, is the angle that comes from the device I have on my belt that I'm going to show you in a second. And those are other tests that I did that are pretty much the same. So I was flying at full speed, then I was pulling the brakes around here, and here I was getting really close to the stall. The thing that is that velocity start to decrease. I change the shape of my canopy and the angle of attack goes up. At this point we have to see if when the angle of attack goes up, we also have an increment in the lift and drag coefficients. Let's have a look. Some other data like lift coefficient and drag coefficient. So in this case we have lift and drag coefficient, orange and red lines. This is the pitot velocity I was saying before. So no brakes in this part, we get a lift coefficient of around 0.55 and we have a drag coefficient a little bit less. When we pull the brakes, okay, when we slow down and we increase our angle of attack, which is this black line right here, we get an increment in both entities. If we go closer to the stall, we have also an increment in both coefficients, but at this point we have the drag coefficient going much higher than the lift. This is because in this condition the canopy is not able to give us good performances. Okay, this is the stall and the canopy almost loses all the forward velocity. I repeated the test another couple of times here as well. So we have no brakes, we start to get slower and slower, and we have an increment in both the coefficients as well as the angle of attack. With my airspeed sensor, we are also able to measure the wind components. So if you are wearing a GPS and nothing else, you cannot measure the wind. You only get the ground speed. With my instrument, combining the two, we can get the TAS, which is the true airspeed or the pitot speed, call it as you want. We also have the ground speed measured by the GPS, and of course we can find the wind. In this case I was flying at more or less 30 kilometers per hour, pointing 80 degrees. So this is north, this is south, east and west. I was traveling this direction with a wind component about that direction at 50 degrees, pushing me 46 kilometers per hour with a resulting ground speed of 75 kilometers per hour. So this is pretty useful because knowing where the wind comes from and how much is its intensity, we can understand better the performances of the canopy in different conditions. So now we start looking finally at the performances. In this plot we have the lift coefficient against the angle of attack, and we have a set of three different data sets. The first one around here is the CL where we were flying without putting any brakes. This is the set of data with more or less 50% of the brakes, and this is a really a condition really close to the stall. So as we can see here, we have some kind of degrees of inaccuracy because I mean we are doing experimental aerodynamics, so there are some external factors that can influence our readings and our data. So for a CL of around 0.55, we have an angle of attack of around between 2 and 0. Then if we want to go up from around 15 plus minus couple of degrees, we have lift coefficient of around 1, and we get the maximum lift coefficient of around 1.2, 1.3 when we pull the brakes really hard, we get close to the stall and the canopy is flying at 25 degrees of angle of attack. The same can be done for the drag coefficient as well. I forgot to mention that we also have the equation with the main coefficients right here. And same, drag coefficient, as you can see, a little bit lower compared to the CL, and that's a good sign when we fly with no brakes. Then we go up, we pull the brakes, and close to the stall we have 1.3, 1.4 drag coefficient at 25 angle of attack. The last plot I want to show you for this video is the drag polar. This is the main plot when it comes to study the aerodynamic performances of a wing, or in this case of a canopy. Why this is important? First of all, with this kind of curve we can study the stall behavior, we can study the best point of maximum efficiency of the canopy, and based on those data we can modify the shape and see how those modification affects the lift and the drag of our canopy. Since the efficiency of canopy is lift divided by drag, or CL divided by CD, with this plot we can understand a lot of things about our wing. So you see the blue dots, which are the experimental data, and the red line is an approximation of those. We have this portion of the data where we were with no brakes, 50% brakes and stall. So we can extrapolate the equation. So we have 0.05 of drag coefficient, which is the minimum drag right here of our wing, and then we can see how the behavior and how the inclination of this curve is. For example, in our case, if we want to design a canopy for a new skydiver, we don't want a type of parachute that is giving us a sudden stall. For example, something like this that is going down pretty fast. We want something more soft like this, more gentle. So if you are new to this sport and you get close to the stall because you've pulled your brakes too much, you don't want your canopy to close completely, but you want something more soft and gentle. On the other hand, if you want to design a high performance canopy, this curve is going to be totally different. I want to show you one last thing, which is the drag polar, but without using the airspeed sensor, but only the GPS. So if we want to use only a GPS, we cannot consider the wind component, and we don't know the true airspeed at which we are flying the canopy. So as you can see, we have here the drag polar with all the data coming from the true airspeed, and here we have the drag polar considering only the ground speed, so without any wind. We don't know on this plot what kind of true airspeed we are flying at. So as you can see, the data are more scattered. The approximation of the curve is not precise as this one here, and the coefficients are wrong. We got 0.09 of minimum drag compared to 0.05 in this case. So what I wanted to underline to you is that you can extrapolate some data using just a GPS, but make sure to double check with an airspeed sensor, because if you want to really know the precision of your performances, you need to know your true airspeed. So in this case, those are the final results, where you have the differences between using a true airspeed to calculate your performances like CL and CD, and this which is basically use a GPS and measure your ground speed and not considering the wind at all. So hope you like the video. This is the way I manage my data. I do the test, I create some sensor, and hope you guys like it. If you want to see more like this, let me know, and